אוקיי.
נתחיל
זה
אוטומטי.
כאילו אוטומטי?
כן.
זה מה שאתה צריך. זה מה שהתכוונת, אוקיי.
לא,
חשבתי שאתה מחבר לי את זה למחשב.
לא, זה מקליט את זה. את רוצה את זה או לא נוח לך? מה שבא לך. אם זה בסדר לך, אז תשימי את זה בכיס.
זה עדיף, זה הבעיה.
זה פה משהו. נראה לי לשמור את זה טובה.
בסדר? שומעים טוב? כן.
אני מעלה את זה לערוץ יוטיוב, זה נהיה בדרך כלל ויראלי בין 8 ל-10 צפיות.
יואו, מדהים. אני מקווה שאביב יהיה אחד מהם. חסר לו שלא. מה? הכל בסדר.
Hi everyone, so it's a pleasure to introduce Keren in the Weizmann Institute. Keren did have a bachelor here, and then master and PhD at Weizmann Institute. She recently graduated and moving to the Netherlands soon.
Yes. Thanks, Guy. So it's really nice to be here. Very nostalgic for me. I graduated here about 7 years ago, so it's nice to be back. And yeah, and today I'll okay, I'm gonna start. Nathan can fix stuff. Right, so today I'll present to you my PhD work and parts of my PhD work, and hopefully I will have a few minutes left in the end to show the research that I did in the last couple of months during my first postdoc at Weizmann that was conducted for approximately half a year. And yeah, so I'll talk about simulations of deep jets and circulation on giant planets. So basically I'm working on atmospheric dynamics on gas giants, mostly Jupiter and Saturn. And this work was, of course, with my PhD advisor, Yochai Kaspi, which is this guy here that some of you probably know, and Eli Galanti, which is a staff scientist in our group, and Nimrod Gavriel, a fellow student that helped me with some of the stuff that you will see today. Right, so why do I even care about atmospheres of giant planets? Well, for me, it's really fun to learn about them because they're really big. They rotate really fast, right? Approximately 2.5 the rotation of Earth. And they're very clean. We have no disturbances, no lands, no oceans, so we can learn about ideal large-scale dynamics. And we know that they're very stable. We have measurements of the zonal jets for approximately 80 years now, and we know that they've been incredibly stable with time. So this is kind of remarkable that we have that. And here you can see pictures of the zonal jets of Jupiter, emphasizing this huge large-scale dynamics that we want to learn about. And I'll present the research question in a second. But before, let's define an atmosphere of a giant planet, right? Because here it's pretty straightforward. We have the land, the ocean, and above this we have the atmosphere. And on a gas giant, that's somewhat a vague definition. And what I'm referring to when I'm saying an atmosphere of a gas giant is the region that is associated with zonal jets, meaning everything that rotates with a velocity that is relative to the velocity of the solid body rotation. So you can say that below the zonal jets, Jupiter is rotating as it would have, as if it would be a solid planet. All right, so how the atmospheres of this planet looks like. Here we are looking at the zonally average zonal wind profile. This is latitude, right, North Pole, South Pole of Jupiter and Saturn, and the velocity value in meter per second. And we see a lot of similarities between the planets, of course some differences that I will point to you later in this talk. We have very strong equatorial jet to the east, so it flows with the direction of rotation. That's called superrotation. This, of course, is not the case here on Earth. And above that, we have this alternating pattern of zonal winds. So retrograde, prograde, eastward, westward. Jupiter has almost 20 of these. Saturn has a little bit less. But we have this really interesting pattern of flow that is switching its direction every few latitudes, every couple of degrees. And we can add to it the values of the eddy fluxes. So let me briefly define this. So if we take the zonal velocity, we decompose it into an average value on disturbances. This would be the eddy term that I'm referring to. And this is the zonally average zonal wind, the profile that you currently see here. We can do this on the other components of the velocity. And one of the terms that we are left with in the zonal momentum equation is this term, which is the convergence of eddy momentum fluxes in the north-south direction. And for those who are not used to look at this equation, here you have somewhat of an illustration showing the disturbances that are converging in the north-south direction, and they would transfer momentum to the mean zonal wind in the eastward direction. And if they are diverging, it would push the momentum towards zonal wind to the west. All right, so this is just definitions. And now we can add this to the graph and look at the value of the convergence of the eddy momentum flux compared to the zonal wind. So these measurements were taken by the Cassini spacecraft at around 2000, 2005, and we reanalyzed them to show this together to reveal this pretty straightforward correlation, at least at mid-latitudes, which basically can say to us, we can also add the correlation coefficient at mid-latitudes. You can see that it's relatively high. This was a single measurement, right? So we don't really have a good estimation for that, but still we can say that the correlation here is very good and that the jets at mid-latitudes are driven by turbulence. That's what we get from this plot. And what we want to ask is what happens beneath the cloud. We had that picture for, let's say, approximately 20 years now, and we had no indication of what's going on below the visible cloud layer, how the zonal jets behave, how the eddies behave. And this is what we're going to answer, at least partially today. And we're going to use measurements from the Juno mission to try and do that. So I was lucky to do my PhD during the time that Juno arrived to Jupiter. Juno is an orbiter. It orbits Jupiter nowadays. So it's been there for approximately 8 years already. And it has 9 different measuring instruments. I'm going to present 2 of these, the gravity science and the microwave radiometer. Specifically, I'm going to discuss about the microwave radiometer measurement. And here you can see pictures of Juno before it went on its way. So this was approximately 2010, showing Juno in the lab. So here you have the 6 different channels of the microwave radiometer. So we have 6 different antennas measuring a different microwave wavelength. So here we have 5 of these, and this is the 6th one. So huge antenna occupying the entire size of the spacecraft, which allows us to probe beneath the clouds. So let me try to give you intuition for that. So, of course, using visible and infrared measurements, we can understand what's going on at pretty much the depth of the cloud layer. And using the microwave, we can probe deeper regions than that, because the microwave measurements are sensitive to the brightness temperature, the opacity of the atmosphere. So where Jupiter is mostly opaque, we would get a large signal in microwave measurements. So using these, we can understand the atmosphere approximately up to a depth of 100, 1,000 bars. Then, using the gravity science, we can understand where we have large mass anomalies, so it can indicate to us on much deeper regions, approximately up to 100,000 bars. And we can also use something like the magnetic field to probe the atmosphere even deeper than that, where the fluid is already completely ionized. So let me quickly summarize some results from the gravity experiment, which I have been a part of some papers that we had on the subject, but today I want to focus on the different type of measurements. So I'm just summarizing what we found using gravity. So we learned that the zonal jets penetrate thousands of kilometers into the atmosphere. Here you have so this is an actual graph illustrating how the jets penetrate inwards. on Jupiter and on Saturn. So on Jupiter, they penetrate 3,000 kilometers, approximately 5% of the radius of Jupiter. And on Saturn, 9,000 kilometers, approximately 15% of the radius of Saturn. They are in the direction that is parallel to the rotation axis. They penetrate the atmosphere in a pretty barotropic way, so we have almost no variation in the z direction. And we know that the results are very statistically robust, so we had some papers about this showing that there is no other explanation for explaining the gravity field measurements. So we're pretty confident that this is the picture in Jupiter and Saturn. I didn't mention, but Saturn we used, of course, not the Juno measurements to do that, but the Cassini measurements, which was a spacecraft that orbited Saturn for almost 20 years. All right, now let me switch to the microradiometer. So this is a picture of Jupiter's atmosphere. What you see here is the ammonia concentration that we got after the very first time that Juno arrived to Jupiter. So Juno has this polar orbit. That means that it approaches Jupiter from the North Pole and exits through the South Pole. And so at each time, at each orbit that Juno does, we have measurements from pole to pole. So here we are looking at ammonia concentration. And of course, we can see different features here, which are very interesting, specifically this very strong equatorial plume. But I want to focus on the small-scale variations that we have here and ask if we can learn about this small-scale variation from dynamical constraints. And let me show you this now in a more graphic way. So again, Jupiter's clouds, the zonally average zonal wind, and here we're looking at brightness temperature from one channel of the microwave, which is located at the very top of the cloud layer of Jupiter. And you can actually see this very nice correlation between the zonal wind and the gradient of the brightness temperature. So this is the correlation you see here. And this correlation is pretty robust over all the 6 channels. So this correlation still holds deep, approximately a depth of 300 kilometers beneath the cloud layer. And we want to explain these measurements using meridional circulation cells, which is something that I'm sure many people here know. So I'm just going to do this very quick overview about meridional circulation cells. So here on Earth, we have 2 types of meridional circulation: thermally driven circulation, like the Hadley cell and the polar cell, and turbulent driven circulation, like the Ferrel cell. So while thermally driven circulation needs to have a hot surface or cold surface to drive it, eddy-driven circulation does not need that and potentially can exist on giant planets or any other planet. So this is the classical dynamics showing from illustrating the Ferrel cell. This is from the Wallis book. And here at the top we have the zonal momentum equation, zonally average zonal momentum equation. So the different terms here are the acceleration of the zonal wind, the Coriolis force. Sorry, I don't have a pointer, so I'm pointing to the top. It's fine. I can use my marker, maybe. There you go. So acceleration of the zonal wind, Coriolis term, the eddy momentum flux convergence, the one that we saw before, and the friction term. And we have no reason to believe that this could not exist on other planets. Of course, we need something else to counterbalance the Coriolis force at the bottom, because we don't have surface on Jupiter. So this could be replaced, for example, something called magnetic dissipation or something like this. Is that kind of it? Okay, sababa. Thank you. But again, this picture can hold. So now let's see how this cell would look if it would transport mass, which is something that people don't tend to consider when we talk about Earth from different considerations. But let's assume that it would transport mass. So if we look at the background mass gradient, this is the ammonia gradient that we know from other measurements. So this is the background ammonia gradient at Jupiter. And we notice that it's not only going to the positive to negative values. It has this region of local minimum due to interaction between water and ammonia. So this is something unique to Jupiter or to giant planets. And then we can add to it the transport direction associated with the Ferrel cell. So we find, comparing to the background concentration, that, for example, the updraft would cause local regions of anomalies. Their sign would depend on the direction of the velocity of the updraft or downdraft compared to the sign of the background gradient. So, for example, this updraft would cause here positive anomaly and here negative anomaly, but it would cause maybe a detectable anomaly if it would be strong enough. So now let's go back to the measurement and see if we can identify this. So I added here two more lines, the vorticity and the eddy momentum flux convergence, and I'm going to assume that the position of the feral cells are dictated by the vorticity or they are just associated with the zonal wind, and their strength and direction is going to be dictated by the eddy momentum flux convergence, which is the momentum source of this equation. And now I can add these to the plot. So you can barely see this because of the projector, sorry for this. But in the background you have these colors of red, blue, illustrating where a feral cell would be on Jupiter, assuming only the dynamics above. And then we're comparing it to the observations and find this almost complete match between the theory suggesting alternating array of feral-like cells on Jupiter with the observation. So sorry that you can't see this, but I can add you the direction of the updraft and downdraft that would be associated from such a feral cell. So you can actually find this very nice correlation. And of course, we have a sign shift. This is due to the fact that we have the local minimum that we mentioned earlier of the ammonia concentration. Of course, we are still left with some open questions. We don't know the depth of these cells, so we only have measurements up to 300 kilometers. We don't have anything beneath that. But we saw before that the jets penetrate 3,000 kilometers, so much, much deeper. Maybe the cells also go that deep. We don't have any measurements. We don't know the leading order balance. We only have, again, the values of these we only have at the cloud level. And we don't know how the eddies behave beneath the visible cloud layer, because again, we only had one measurement at the clouds, and this is something that we would want to try to explain.
Keren, can you get what determines the width of those cells?
Sorry?
What determines the width of those cells?
So here we're just used, again, vorticity to decide it, but it would be the Rhine scale. Thinking about eddy-driven jets at mid-latitude.
Does it agree with
It is. It's pretty good. All right. Before I go to try to explain the open question, let me just try to visualize for you what is the implication of these findings. So compared to the classical pictures of the 3-6 cells on Earth, we now have a similar one for Jupiter, showing this pattern of alternating feral-like cells at mid-latitudes. So the measurements allowed us to estimate that we have 8 of these in each hemisphere, so 16 total. This alternating pattern of feral cells, so the feral cells that we have on Earth, but also to the other direction associated with divergence of eddy momentum flux and not just convergence. And NASA, so a lot of people from the Juno mission were a part of this study, and they suggested that they would prepare a video for us, so we said yes, okay, and then we had this nice video that people in JPL did for us, showing how this pattern of feral-like cells looks like if we would be able to see them. So illustrating here the velocity components, showing how robust they are in the climate of Jupiter. Okay, so to answer the open questions from before, we're going to use a different methodology, and we're going to use a deep, high-resolution general circulation model for gas giants. So for those who are not familiar, just visualize if you solve the atmosphere of Jupiter on a grid, and we're going to solve the momentum equation, an energy equation here written for entropy, and the magnetic induction equation for a gas giant. And specifically, I'm using a model called the Riley code, which solves these in a spherical shell. using spherical harmonics. And our setup is for fast rotating, compressible, convection-driven dynamics, because this is what we believe we have on both Jupiter and Saturn. And this way to write the equation is pretty straightforward with using non-dimensional parameters. And these are the different parameters that would decide how the result would look like. So we have, for example, the Ekman number showing the relationship between the viscosity term and the rotation terms. Here, so for example, you can see omega, which is the rotation of the planet. Viscosity, in this case, of course, the numerical viscosity that we need to introduce to the model, and a typical length scale.
But L is not the radius.
No, it's not.
It's not
No. All right, so let me jump ahead and show you the result of such a simulation when we try to compare it to Jupiter. So here we see the 3D sphere at two different depths. So at the outer radius and inside, close to the inner boundary of the simulation of such a simulation. On the right-hand side, we have the zonal wind snapshot, and on the left-hand side, we have zonal and time average zonal wind. So you can see that the model is very turbulent, right? We have a lot of small-scale features here, which of course can be gained only if we're using relatively high resolution.
What do you mean by high resolution? What's the resolution?
So it's a kind of a third of a degree.
What's the distance in Jupiter?
So in Jupiter, a degree is 1,100 kilometers, so that would be 350 kilometers approximately. Yeah, so this is high resolution when you think about gas giants. Of course, we don't solve any small-scale dynamics here. But again, talking about gas giants, that is considered high resolution. And we can see these relative small-scale features here, or turbulence, as we sometimes call it in the atmosphere. And of course, taking its average, you can see this nice pattern of alternating east-west jet streams at mid-latitudes. And we want to start by asking whether these jets are eddy-driven, which I already implied from the previous pictures that they are, but I want to quantify this. So again, I'm showing the same equation that we saw before for ferrous cell dynamics, right? So acceleration, Coriolis, two terms of eddy momentum flux convergence, because now this is a 3D picture. I need to include the other term as well, so the radial eddy momentum flux, and the viscosity. So we don't have a drag like bottom friction with the surface as you would have on Earth, but we do have, of course, viscosity that's going to be important in numerical simulations. And this is a shell looking at, so again, taking the zonal average of the velocity field, this is what you get, showing this in the direction, this is the direction parallel to the rotation axis, and this is the radius, right? Okay, so let's see if these jets are eddy-driven. Let's add these two terms to the plot here. And we can see this is their summation, and we can see this perfect correlation between eddy momentum flux terms and zonally average zonal winds, basically saying, yes, these jets are eddy-driven. But more than the fact that we can say that they're eddy-driven, we can now see how the different components are building these jets. So very close to the top layer, we have the meridional term, which is the important one, transferring momentum. This is the term that we have measurements for on Jupiter and Saturn, right? And much deeper into the atmosphere where the density increases, so maybe I didn't mention, but this is an elastic, we have density variation with depth. So where the density increases, we have actually much more important term of the radial flux, which is something that you would expect. So I didn't wrote the anelastic formulation here, but this is the one that we were solving for. So you can imagine that you have this rho bar inside the divergence term here. Okay, what about the meridional circulation? So we saw that the jets are eddy-driven, but we want to now to visualize the meridional circulation. So here I'm plotting the stream function, the meridional stream function on top of the zonal jets. It's a bit hard to see, so let's focus only on 4 different jets, 2 in the northern hemisphere, 2 in the southern hemisphere. And you can see the alignment of the meridional circulation with the jet streams. And now let me focus on just one of these to explain the different branches. So this is an illustration based on the dynamics that we see here for an eastward jet in the northern hemisphere and its meridional circulation. So the jet is to the east, in this case to the page. And what we can see here at the top of the circulation, of the bottom circulation, is that indeed we have a balance between the Coriolis force and the eddy momentum flux convergence, exactly the same one that we can see at the cloud top of Jupiter and Saturn. And at the bottom branch, we actually have a balance between the Coriolis term and the radial viscosity term, which is going to be large depending on the boundary condition that we chose for such a simulation. So in this case, it is large enough to counterbalance the Coriolis force closing the circulation. But the circulation is, the model is symmetric, so we're using the same boundary condition top and bottom. So the same balance exactly we have at the top branch, resulting in reverse circulation. So we actually ended up with this stacked pattern, this stacked circulation pattern of two cells rotating in different directions, bottom and top. And of course, we can compare it to the classical picture. So the cell at the bottom is completely equivalent to what we have here in a ferrule cell. And I didn't mention this earlier, but from different evidence, people think that we do have reverse circulation above the clouds of Jupiter. So in the very, very thin atmosphere, approximately half a bar and above, there is indication pointing on a reverse circulation. So while radial viscosity, of course, cannot really balance anything in reality, it does imply that if we would have something that is resulting in some kind of a friction term at the very top of the atmosphere, for example, a tropopause or very sharp density variation, then we could result in this reverse circulation. Okay, let me... Yes.
Sorry for that. So your argument is, so you've done this for the sake of the simulation, but the boundary of the top may not actually be very true to life.
Also at the bottom, if I'm being honest, I don't expect that in the real life radial viscosity can counterbalance any real physical term. But in the simulation, this term is always very large because we have to force the simulation to get reasonable spin at time. We're using orders of magnitude higher energy source than we have in the real planets. So we have to counterbalance this by orders of magnitude larger viscosity, which then obviously would result in very large terms. But again, try to understand viscosity for a 350 kilometers box. That would need to be a large term. This is not the molecular viscosity as we used to think about it in the equation. Okay, let me summarize the part about the mid-latitudes and devote the rest of the time to talk about equatorial dynamics. So at the mid-latitudes, we saw that we have 16 meridional circulation cells that are similar to ferrule cell dynamics at the mid-latitudes of Jupiter. We don't have evidence for the meridional circulation on Saturn, but we have no reason to believe this would be different because at least at the cloud top, they look very similar to each other. And each one of these cells is paired with an alternating jet stream, right? One to the east, one to the west, resulting in this reversed circulation pattern. And then we were able to reproduce something similar to that picture in a general circulation model. And using this, we were able to learn about the structure of the eddy terms beneath the clouds. And, for example, one of the open questions that we presented before is that we don't know how deep the cells penetrate, right? We only had evidence for the upper 300 kilometers compared to the jets, which are 3,000. So the simulation teaches us that actually the two are associated with each other completely. So we would expect that the circulation would penetrate the atmosphere as deep as the jets penetrate. We can't prove that, but that is what the simulation suggests. Okay, equatorial dynamics. All right, so now I'm plotting again Jupiter and Saturn zonally, average zonal wind, but now it's to scale. So now the y-axis is the same between the two planets, and suddenly I'm sure everyone noticed that Saturn has much stronger jet than Jupiter, right? So the jets on Saturn reach almost 300 meters per second, and on Jupiter it's approximately 100 meters per second. So it's 3 times stronger, and it's also much wider than the equatorial jet on Jupiter. And we want to ask if this has anything to do with the fact that we know that the jets on Saturn penetrate much deeper than they penetrate on Jupiter. So again, Jupiter 3,000 kilometers, Saturn 9,000 kilometers. Again, this 3-to-1 ratio, but on the other direction now. And actually, no, not to the other direction, the same direction. So Saturn 3, Jupiter 1. And I'm also plotting here the tangent cylinder, which is basically the position, an imaginary cylinder where the atmosphere touches the interior. So we can project this cylinder to the cloud top. And everything that I'm talking about now, the equatorial dynamics, is outside from the tangent cylinder, towards the equatorial region, so only these dynamics, what we haven't talked about before. So I want to try to understand if these two are connected to each other. And for that, I need to consider what can influence the strength and width of the equatorial jet stream. And we know that some stuff definitely would affect it. For example, the rotation rate. So planets that rotate much faster would result in much stronger equatorial jet streams. But we know that Jupiter and Saturn has nearly equal rotation rate term. And we know that the thermal forcing, or the energy source, again would result in much stronger equatorial jet stream. But again, this is almost equivalent between Jupiter and Saturn. So considering the physical parameters, we have no reason to believe that they should be different than each other. Of course, in the simulation, other parameters such as the numerical viscosity, which we discussed, can also strongly affect the result. But even when simulating Jupiter and Saturn, we have no reason to believe that they would be different than each other. But we do know that the jet stream penetrates much deeper in Saturn compared to Jupiter. And the methodology to check this would be to perform simulation with varying the simulation inner depth, so varying the layer where we finish the simulation, making it deeper and smaller, while make sure that the other parameters are constant. So we don't want to vary the rotation rate or the viscosity or something like that. So we make sure that all of the control parameters remain constant while varying the wavelength, the sum of the length of the simulation, the typical length.
How do you keep L?
So L is changed, and then we changed, so we don't change, for example, the rotation, but we do change the viscosity term, for example, between the different simulations.
So you change the viscosity?
Yeah.
The caps, so you and cap are both change?
Yes, everything is changing to make sure that Rayleigh number, Ekman number, and Prandtl number would stay the same. And these are results, for example, from 10 different simulations with different L, all right? So different shell depth. And this is 10 different simulations showing the same dynamics, the same large-scale dynamics. So here we're talking again about convection-driven equatorial superrotation. And we can try to estimate. So here I'm asking, is the depth of the simulation affecting the width of the equatorial zonal jet? So you can already see that yes, but I want to quantify this. So I'm defining the latitude that's going to represent the inner shell depth, the L basically, and I'm going to define it using a latitude. And I'm going to define a latitude that's going to estimate the extent of the equatorial jet. And I want to compare them, and I get this pretty remarkable one-to-one correlation. So absolutely, it completely agrees with the idea here that all the 10 different simulations are sitting on the one-to-one ratio, including Jupiter and Saturn. So I do have these numbers for Jupiter and Saturn. I do know what is the depth of the simulation, or not simulation, the depth of the zonal jets, and I know what is the width of the equatorial dynamics on Jupiter and Saturn. So I can compare these together and say that absolutely the width of the equatorial jet has something to do with the fact that the zonal jets on Saturn are much deeper. And now let's understand exactly the mechanism that is controlling this. So when we're talking about fast rotating convection setup, the dominant term in the momentum equation is going to be the convergence of eddy momentum flux that are directed perpendicular to the axis of rotation. This is the per term here. And this is an illustration of these terms. So we're getting these very large-scale cylinders that are completely straight, that are tropic from north to south, and they're symmetric, and they are tilted, you can see it here, in the prograde direction. And then their convergence are going to transfer momentum to the mean zonal wind term, resulting in superrotation. And after we consider this, we can go back to the simulation and look at the different terms. So here we have the zonal wind of one of the simulation and the convergence of the fluxes that are perpendicular to the axis of rotation. And again, we can see the momentum source for this zonal wind. Here, exactly what we saw before, but now illustrated to compare it with the different terms. So outside of this dashed line, we have convergence of eddy momentum fluxes resulting in eastward zonal wind, and towards the interior we have divergence resulting in negative zonal wind. And according to this definition, this was where we decided that we're going to assume the width that we used in the plot before to compare to the theoretical value. So there is a mechanistic explanation for why we choose this depth. This, of course, you can see how the column looks like in the equatorial plane. I'm going to jump ahead. So now we want to understand if the strength of the equatorial jet also has something to do with the depth of the domains. So here we're looking about the strength of the zonal jet with latitude and with radius, normalized radius in this case, so with depth for the simulations from before. And now we want to compare it to the strength of the eddy momentum fluxes, right? Because we saw that this is the mechanism resulting in the zonal wind. So we want to estimate this as well. So estimating this on the radial plane direction at the equatorial plane, we get this plot again. So this is the strength of the eddy momentum flux, not the convergence. And we can already see this very large trend, again, exactly as we see here. So making the simulation shallower, you would result in much weaker eddy terms or vorticity from relative small scale that are probably connected to each other. And again, we want to compare the different plots. So basically saying we are comparing this plot to this plot, and again, we get almost this 1-to-1 ratio. Basically saying that the strength of the zonal wind is also associated with the depth or the volume of the atmosphere, allowing much stronger eddies to evolve, forwarding more momentum to the main zonal wind. Yeah?
What is the boundary condition at the bottom?
So in this case, it's different than what we saw before, but in this case, it's free slip. So
it is free slip. So,
yeah.
So you can say that if it was a no slip, you could say that as you make it deeper, you just by definition.
Of course.
So
In this case, it's free slip.
So you don't think there's a relation between the viscosity of the surface and
I don't. No, before it was no slip, by the way. But in this case, it's not. Okay, so let me summarize this, and if I would have, how much time do I have left?
10 minutes or so.
I have that. Great. So let me summarize this quickly and use the last 5 to 10 minutes to tell you about ice giants. Right, so we talked about this 3-to-1 ratio between Jupiter and Saturn. So we have the penetration depth of the flow field, which is 3-to-1 in favor of Saturn. We have the maximum equatorial wind at the equator, equatorial wind, of course, again, 3-to-1 ratio in favor of Saturn. Also, we have the cylindrical projection of the retrograde jet. This is the definition, what we said before, of how we would choose the width according to the mechanism considered here.
Which gives us the momentum flux, right? The eddy momentum flux.
Yeah, the eddy momentum flux.
That's projection.
Yeah. And also, I'm showing here the electrical conductivity, where it reaches value of 1 Siemens per meter, where it is expected to start influencing the zonal wind approximately at this, once it's reached its value. So also considering this, again, we have pretty much the same value resulting from this. And all of these are compared to the fact that Jupiter is much heavier than Saturn, approximately 3 times heavier than Saturn, resulting in much denser gas closer to the cloud layer. So that could potentially explain this pretty remarkable relationship that we keep on getting from different estimations that are being done now for Jupiter and Saturn. I keep on pressing this, hope it will change slide. Okay. So yeah, 10 more minutes to talk about ice giants. So this is work that I'm finishing now. So if anyone has any input on this, I would be happy to get it. And what you can see here is the zonal wind pattern for Jupiter and Saturn, which we already discussed about a lot. And I'm also adding here Uranus and Neptune, which are the ice giants. They're farther away in the solar system, very small solar radiation values. And of course, there are many differences between the ice giants and the gas giants, but I want to focus on the equatorial dynamics, showing that here, as we talked before, the zonal wind is to the east with the direction of rotation, resulting in superrotation. Superrotation basically means that we have more momentum at the equatorial region compared to if we only have the planetary angular momentum. So we have this extra value, meaning that we have to have some momentum source giving momentum to the equatorial region because it could never be generated only considering the planetary angular momentum. But on Uranus and Neptune, this is not the case. They are retrograde. They are subrotating as Earth, which has no, violation of momentum. And from that reason, people often treated the ice giants completely different than they treated the gas giants. So almost all theories explaining these differences have focused about the fact that it should be a different mechanism between the gas giants and the ice giants. And I want to argue the opposite. I want to argue that they are actually completely equivalent to each other, and we should consider a different mechanism that can explain the equatorial wind on both, because they have very similar parameters. For example, the rotation period is large in all of them, so Uranus and Neptune are also fast rotating, not as fast as Jupiter and Saturn, but definitely fast enough that we would think that rotation should be dominant in these planets. We can look, for example, on the thermal emission that is normalized by the insolation, and we get almost exactly the same value for all 4 planets, meaning that the energy source is pretty much equivalent between them. And of course, we can look about the penetration depth of the zonal wind from both gravity estimation and from ohmic dissipation, magnetic field estimation. And again, we're resulting in these very similar values. So we know that Saturn is 3 times deeper than Jupiter, but Uranus and Neptune are equivalent to Jupiter. They almost result in the same value. Upper 5% of the planets are associated with zonal winds in all Jupiter, Uranus, and Neptune. So considering all of this, I think that we should think about a different mechanism that can explain all 4 of them together. And this is the same mechanism that we saw before, right? The columns in the direction of the rotation axis that are tilted in the prograde direction, giving momentum to the mean zonal wind. This is straightforward. But what I haven't talked to you about, what I haven't told before, is that the tilt of the convection column has something to do with the fact that we have with the boundaries. So in this case, to get this solution, tilt to the prograde direction, we have to have curvature boundaries. We have to have boundaries that are convex. So where is the marker? Right. So if it wouldn't have any preferred boundaries, if it would be completely like an annulus, the solution, the result here of the equation, the linearized equation, can be to either side. We would get a result that is both plus and minus the velocity field. So we would be able to have tilt to the either direction. But if we do include the boundaries, and we know in this case that we have curvature boundaries, convex boundaries, then the only solution is the positive one. And of course, trivially, if the curvature would be to the other side, so this would be the convex, And with this would be the concave boundaries. So in the concave result, we would get the negative value, all right? Tilt to the other direction.
How would you concave top of the atmosphere?
Very good question. This is exactly the illustration that you have here, right? So in theory, if you would have concave boundaries, then you would result in tilt to the other direction. But of course, in a sphere, which is what I'm solving for, we don't have concave structure. We have convex structure. But what I wanted to ask is maybe if we go to shallow enough atmospheres, so taking L to be very, very small, maybe because you're so squished against the outer boundary, maybe you just don't feel the boundary, the curvature. And surprisingly, it worked. So these simulations are relatively with a shallow L. This is 0.94, okay? So pretty equivalent to both Jupiter, Uranus, and Neptune. And the simulations here are completely equivalent to each other. So basically, talking in numerics term, people that work in numerics, it's the same input file for both simulations. The only difference between them is the random initial conditions, which are here are just random noise. I'm using very small scale random noise, and I get the opposite picture if I'm solving for a very shallow atmosphere. So the statistic, by the way, to receive this and this is almost equivalent. So I run this for 30 or 40 experiments, and 60% I got superrotation, and 40% I got subrotation, right? So pretty similar statistics. So both solutions are plausible, which made me think that this is a bifurcation problem. And in fact, we could reach either solution depending on the mu parameter. Let me show you, of course, the eddy momentum flux term, which I'm sure you already learned that I like. So here is the eddy momentum flux compared to the zonal wind. And here you can really see that this is like looking at the cylinder. Here you can really see that it reaches the boundary, the curvature boundary. And here you can see that it doesn't. So it really is concave structure of the column, living within a spherical shell. So there is probably some competing mechanism that result in the fact that it doesn't reach the boundary, but it doesn't have to compete it, because in the other scenario it does reach the boundary. And here showing the tilt, so here as expected in the prograde direction, and here to the other side, retrograde direction. You can also really see it here, looking just at the zonal wind value. This is to the east, and this is to the west.
So you don't mean that it's concave, but you mean that there's no condition imposed by the convexity of the surface.
So the cylinder itself is concave, and it has to be concave to conserve potential vorticity.
It doesn't reach it.
So it doesn't reach the boundary yet.
So the implied force or condition imposed by the convexity doesn't apply when it's very shallow.
Exactly.
That's what you're saying.
That is what I'm thinking, yes. And we wanted to estimate the bifurcation problem and see where it holds. So same experiment as before. We kept the control parameters constant and changed the depth of the convective envelope. And this is what the picture that we got. So this is the normalized inner radius, L, just in different terminology here. So how deep we are. And we did experiment by taking the result from before, so taking these, and then after it reached steady state, then we varied the domain depth. This is shown by the dashed lines. So dashed blue lines is the subrotation result, the subrotation initial condition, and the dashed red line is the superrotation initial condition. And then we got this remarkable what's called a back-to-back southern node bifurcation. So we have two stable branches, the superrotation branch and the subrotation branch. So if we go very deep, then there is awareness to the concave structure of boundaries, to the convex, to these boundaries. If the cylinder is basically large enough, it is aware to its geometrical boundaries. resulting in only superrotation. So even if you would start making everything in the sub-rotation case, the columns would completely be sheared.